This video is entitled Finding the Area of a Region Between Two Curves. Now by this point in time, you've probably seen the basic definition of just finding the area under the curve. That all comes from, in theory, the Riemann sums and the sum of all those rectangles, which leads to the definite integral. Now the basic definition of the area would be something like, so the graph has to be defined as above the x-axis, and f of x has to be like this, and then you have your a, and there's your b, and finding that area would literally be just evaluating the definite integral of f of x dx from a to b. Straightforward as that. Now, though, we're going to look at two curves, or what if your curve dips below the x-axis, and other little things like that. It's a little more expanding on that same idea. Like here's a picture where it's two separate curves. Technically, the other one I showed you, you can say there's two curves. It's just one of the boundaries is the x-axis, which that's y equals 0. So technically, it is two curves because you do have a boundary there. But I'm talking about where one of them is not automatically the x-axis. So here's a f of x and a g of x, and we'll find that area. Here's one where it's just one curve, the other curve is the x-axis, but they want the a and b are way far outside, so it creates three pieces right here. And then there's another one, two graphs that they would never intersect each other like this first one does. They don't intersect, so you would have to create boundaries. Like for these first two graphs, you could actually solve and figure out where those points of intersection are. This one, they're never going to intersect, so you would have to determine what you wanted, what a and b were supposed to be, or be told what a and b are supposed to be. Now this is the general formula for a single region of integration, where one graph is consistently above the other graph for the entire region a to b. Now the formula is written as f of x minus g of x, but you have to be real careful don't treat that as an absolute. In other words, what I wrote down here means upper and lower. That's a little more accurate, meaning on that region, one of them needs to be the upper, the higher y value, than lower. So it doesn't matter. The naming of f and g are irrelevant. It's whichever one's upper minus lower, and that's what Stewie's giving us a little warning right there. It's possible that if they name two functions f and g, that it literally wouldn't be f minus g. Of course, if you get 0 or a negative answer for your result, then you've done something wrong anyway, because the answer for area has to be positive. Definite integrals in general can take on any real number value. 0, positive, negative. But if you're finding area, you must absolutely get a positive answer. All right, so let's look at this example. Now, sometimes the problems will put in boundaries, or sometimes you find the boundaries yourself. Now, this is one where we are given the boundaries. X equals -1, x equals 1. Now as you can see though from graphing this, that there is a point of intersection, a natural point of intersection on the left side, but there's not one on the right. And I think that point of intersection on the left side is kind of a weird number, where it's not nicely solved by algebra. I generally try to avoid that kind of problem on a quiz or an exam, but anyway, so the graphs, it's kind of sketching the graphs with a calculator's fine, or even a rough draft manually would help. Just kind of get a feel for what's going on. So you can see it's only one section, one region of integration. And what I mean by that is, unlike this middle picture up here, where we'll talk about how to handle that whenever one of them it's lower, then it becomes upper, that sort of thing. But this one, the x cubed plus 1 is the upper graph for sure, and the 1/2 x and the minus 1 is the lower graph. No question. So that means we are evaluating these upper minus lower. Now, I work these out kind of old school here, you know, the way I learned how to do this. With the modern technology, I mean, obviously it's good to know how to evaluate a definite interval. You need to for a lot of other reasons. But for this, I don't mind so much if you're just using the technology and work it out that way. You see, I have the upper function minus the lower function. I combined all the terms. I did the antiderivative term by term, plugged in 1, plugged in -1, subtracted, and got 4. But if you see what I did here, now this is the way the F and N down here, this is the way if you have like an 83 or possibly an older operating system of the 84, that's the way it had to be typed in there. So you find the F and N, and you put your function, comma, x. That just means it's with respect to x. So long as you put, obviously, if you put a different variable in there, you have to put a different variable here. Then you put your lower value, you put your upper value, it gives you 4. Now, the slightly newer operating systems, when you hit F and N, brings you up an integral sign. A little more modern looking there, technology-wise. So you would just put the function in there and put the lower. It's more like how you would write it. And you see that also gives you 4. But obviously, you don't need to go buy it. I wouldn't buy a new calculator just if you had to do it this way right here. You know, it's not that big a deal. So that's the old way and kind of the newer way to do it. The answer is 4. That area turns out being exactly 4 square units of whatever the units are. I know it seems weird that with all that curving and stuff, it turns out to be exactly 4, but it is. Let's jump down to the next example. Now this one just says find the area bounded by the graphs. No, there's no axis thrown in there, nothing, don't add anything in there. So literally, so we have to find the points of intersection for this one. Now, if you just want to graph them and find the points of intersection using a intersect command in the calculator, calc intersect, I believe it is, or however, that's fine. But it's you know, doesn't hurt your algebra skills here to practice this, and it's not that complicated either. So I just set these two equations equal to each other, and then brought the right side over to the left side, and then I factor out an x, and I got x times -x plus 3, which I could have got rid of the negative right there and changed it. But anyway, long story short, you get limits of integration of 0 and 3. So it doesn't matter how you come up with that algebraically from the graph itself. Well, in this graph, you clearly see the curves above the line. Now, don't make this as 2 problems in a row where it happened to be the higher powered function was the upper graph. You know, don't ever try to look for shortcuts and think, oh, the higher powered function is always going to go first. That's not true. What if we had an upward parabola and then a line, and we were finding this? So the line would be the upper graph, and the parabola would be the lower graph. All right. So the upper's the downward parabola, the lower's the line. So you see I worked it out that way. I subtracted, combined terms. Yeah, if you were doing this manually, you kind of want to combine like terms before you integrate. It'd be kind of silly to, for example, to integrate a 4x and a -x, integrate them both. It would make it easier to combine them and make them 3x and just do one antiderivative. So I took the antiderivative, -x squared plus 3x, put in 3, put in 0, 0 makes this 0, and I got 9/2, which you can see that also that's what I got when doing F and N. There it is the old way. Obviously, a lot of these, when I created these notes, they were done this with the older operating system, and now I've added in. So there it is, 4.0. 2.5, 9/2, 9/2. I got 9/2 manually, so everybody gets 9/2, and we're happy. 9/2 it is. All right, now this one's a little creative here. So I've added a couple of sort of created, artificial boundaries instead of just letting it, because, this question could have been asked like the last question, where you just want to find the area bounded between the two curves, and we would have done the same thing. Now this one, I actually am finding those points of intersection. We do need those where they intersect, and we'll talk about that in a second. So I did the algebra and found those, and I got -1 and 2. My point being that if I didn't have this last part about those boundaries, we just would have integrated the parabola minus the line from -1 to 2, and that would have gotten the middle section. But any time that you're finding, you're trying to find the total area, especially, and we want the area of all those pieces added together. Anytime the upper and the lower graph change positions, one becomes upper, one becomes lower, you have to create a new integral to find that area region. You cannot integrate this straight from -2 to 3 for these two functions. Because you see, in this first region, the line is above the parabola. In the middle one, the parabola is above the line, and in the last one, the line's above the parabola. So that's why this has to be split into 3 regions of integration, which you would add together. So you cannot go from start to finish in this problem because of the changing of the positions of the lower and the upper. So you see, -2 was a number that I put in there, and the -1 was a number that we found. So this first region is going from -2 to -1. And that region, the line's above the curve. So I'm putting the line first and the curve second. Upper minus lower. In the middle, it goes from these two numbers, -1 to 2. -1 to 2, and that region, the curve's above the line. The curve's first, line second. The next one, 2 to 3, line is above the curve. So technically, that's the result right there written out. And let's see. So you see, I did it manually. Not necessary. You can use the technology, is fine. So let's see what we have here. So I worked them all out manually. What did I get? I got 11/6 for the first one, 9/2 for the middle piece, and 11/6 for the last piece, which adds together to 49/6. Now, one thing we talk about the area having to be positive. See, that's an interesting thing here too. That's why it's important to check each result, each piece, because not only does the total area have to be positive, each piece has to be positive. So let's say you did this and didn't check, and let's say, for example, and you didn't do the picture or whatever, let's say you got, let's say 2 of the pieces had an area of 4 and one of them had an area, well, you got -2, but you didn't check that it was -2, meaning you just added them all together in one step without checking each one. Well, the problem is 4 plus 4 plus -2 would give you a positive number of 6. So you might think, oh, I got this right. It's a positive number 6. But you would have been wrong because the -2 would have been wrong. So it should have been 4 plus 4 plus 2, which is 10. So not only is the area obviously is positive, each individual area must also be positive. All right, so I did all these. I wrote all these integrals in there and I added them separately. Did the math frac thing, got 49/6. I didn't finish it over here, but there's a long way to do that. But the answer is 49/6. Now, how about find the area bounded by these two graphs? So this is a picture of a graph for x cubed minus x and y equals 0, the x-axis. So this one just happens to create, without adding artificial boundaries, it just creates two bounded regions just by the definition of the functions themselves. It's not, so a lot of times they're just one region of integration, but this one does have two because it comes back and turns around. So you got this piece over here and this piece over here added together. So yeah, like I say, you can probably from the graph tell what they are, but I did solve them algebraically. X cubed minus x equals 0. I factor out x. I got negative 1, 0, and 1, which kind of matches the picture. So for this one, we would have curve above the line, so it goes first. And the second one, we have line above the curve, so it goes second. And there we go. So there are the two definite integrals set up. You know, they must both be positive. Now, what I did here, which is something you don't have to do, but what I did right here, just but I wanted to explain what I did, is I just made this that way. I typed in the same function and just changed the numbers. Is I use that property of definite integrals that allows you to get rid of this negative right here in front, I switch the limits of integration. So anytime you reverse the limits of integration, it creates a negative. So what I did is I essentially created a negative that would wipe out that negative. I don't know. It didn't have to do it that way, obviously, but I just did it. But at least I want to explain what I did, even if you didn't do it. And so I got 0.25, 0.25. Each of them are 1/4. So you add together and you get total areas 1/2. Yeah, because this graph is actually symmetric, if you would have done this straight from negative 1 to 1, you would have gotten 0 as the answer. So obviously that would have been wrong. We'd had to have realized that there was two regions there. But like I said before, even if you would have gotten positive, you still could have been wrong. So there it is. Okay, looks like I didn't use the newer, I didn't redo this with the newer looking integral technology. That's all right. You can do that if you want to, and you'll get 1/2. So let's look at this next example. We got sine of x, we got cos of 2x. From negative pi over 2 to pi over 6. Now, the way I like to scale these, now of course, make sure you're in radian mode here. That's important for graphing purposes. Make sure you're in radian mode, not degree. Is use the common denominator, least common multiple between those two, not the common factor, multiple. So it's 6. Of 6 and 2, the LCM would be 6. So that's why I'm using pi over 6. Because that way each little tick mark here, you'd be able to tell. So negative pi over 2 would be negative 3 pi over 6. So you would see it would be exactly 3, and then pi over 6. We'll graph as 1 unit to the right. So I find that easier when looking at trig graphs. Because, obviously they have weird answers. Pi divided by 6 is going to be some, weird decimal number. So that's what I always recommend when graphing trig graphs. Use the least common multiple. So if I had like a pi over 4 and a pi over 3, I would use 12. I would make my scale pi over 12. And that way they would both have the same number of twelfths. All right, I don't like to get too complicated on trig functions. So if I ever had a trig function on a test, you can pretty much guarantee it's going to be just one region of integration. I'm not going to get too creative on that one. So this one forms a nice little one solid region. Now this is a good example of put this in the calculator. Now another way you could do this without graphing it is, since I just kind of verbally gave my guarantee that will only be one region of integration. And that's what's key is guaranteeing one region of integration is what's going to make what I'm about to say true. If that was it'd be wrong when I'm about to say otherwise. But if we know that's going to be one region, then all you got to really do is pick a test point in that region and see whichever one of the y values is larger. And then that would guarantee which is the upper graph. So if you put 0 here, 0 is between those, is in that interval for x. Sine of 0 is 0, cosine of 0 is 1. That means cosine's the upper graph. Now this problem is a good example of what I was talking about at the beginning of this video, is that never trust the naming of the fact it calls it f of x and g of x. Don't ever trust, because that original definition just showed, f minus g integrated. Well, this one's not f minus g. It's actually g minus f, because you're supposed to really go with the idea of being upper minus lower, not f minus g. So this has to go first. But the good news is, since it's one region of integration, and if you knew it was one region of integration, you got it backwards, and you did everything else right, and got a negative answer, then the answer is going to be just the positive number of that. So, all right. Now, there's a couple little shortcut rules here for integrating cosine and sine without having to use U substitution. Save yourself a little time. And that's where it comes from, is U substitution. So the cosine of a times x, which in this case would be 2, antiderivative would just be 1/2 sine of 2x. And that would be the same thing if you just, like say, you let u be 2x and all that. But I'm just trying to save you some time there, and just, if you know that, that'll make things a lot quicker for you. So that antiderivative is going to be 1/2 sine of 2x. And then the antiderivative of negative sine of x, antiderivative of that will be cos of x. All right, so now plug in pi over 6, plug in negative pi over 2. So I did this kind of manually. Let's see what I got here. Now, to technically get what's called an exact answer, which sometimes I like to have people do that on a handwritten test. I guess on a multiple choice test it wouldn't matter as much, because you could just figure out which answer was numerically equivalent to the decimal answer. Now, this is using the Maple software, which is not required for you. In other words, your calculator is not going to spit out 3/4 square root of 3, unless we're, maybe 10 years in the future from when I made this video. Maybe the calculators will start doing that, but at this point in time, in early 2018, the calculators do not do that. But Maple does, though. So I worked it out manually, and I got the same answer that Maple does. So, but if you got the decimal equivalent, that's fine, and then you can look at the right multiple choice answer. So it ends up being 3/4 square root of 3. All right, now we're going to look at something a little bit different here. We're going to look at, suppose that x is a function of y. How do we integrate? We're talking about the rectangles. Vertical rectangles is what we're used to with, the way all that stuff's defined. Let me go back. Well, okay. Pick a color that'll stand out here. I don't know, but all the sum of all the rectangles, that kind of, like I was talking about the theory behind all that. Adding all the rectangles. Well, this one's going to be different. Call these horizontal rectangles. We're now looking at graphs like this. And then let's say we had this coming through here. And then we had a bunch of sideways rectangles, So finding the area like that. Okay. Of course, we're going to use an integral, but I was just showing you what that meant. So now we have x as a function of y. Now these, you have to treat it this way. It's the curve on the right minus the curve on the left. Now, calculators also at this point in time do not graph x as a function of y. So graphing can be a little tricky. You can sketch these sort of by hand. I like to keep these very simple. I don't want to do anything other than lines and parabolas for that reason. So I'm not getting real creative on the nature of what the curve is going to look like for these functions where it's x in terms of y. So you can pretty much guarantee that in my world it's going to be strictly lines and parabolas. It could be two parabolas. And I don't like to have multiple regions of integrations for these either. I want these just to be one nice little section, but I just kind of want to get you feel for how to do this, and then for some of you then that are moving on to Cal 3 eventually when we're doing multiple integration, this is a good skill to have. All right. So I try to keep this basic, but I kind of want to explain the idea, though. It is the right one minus the left one. But like I was saying, if you got them reversed and you did everything else right, then the answer is just going to be the opposite. So if you got left minus right and you got -6, I mean, the answer is going to be +6 if you did everything else correctly. Now notice the limits of integration. This time, I've always been A to B, on the x-axis. Now they're on the y-axis, lower to upper, C to D. Now let's look at this one, kind of a crazy one here. And like I said, these graphs don't have to be perfect here, but well, okay, the one on the right, x equals -y, that's easy to sketch. It's just y equals -x. Now you could, knowing that this is going to be a parabola, I distributed this out, they're going to be a sideways parabola. And here's a little hint for you too, that you don't remember this, that's okay. But if it's -y squared, that means the parabola opens up to the left. If it's positive y squared, it opens up to the right. So what you can kind of do on this, if you like, is if you want to plot some points in there. Now, this time, the way I wrote this is, it's kind of weird, though. Usually when you make these little T charts, you put the X's in, you solve for Y. Just the opposite here. You put the Y's in, and then you calculate, because f of Y is actually X, and G of Y is X. As you see, I wrote right there. So actually, I'm doing, you can't tell, I'm doing, but they still got to be in the same order when you plot the points. So it's still X, Y. So you put in but you plug the Y's first in to calculate the X's. So I just calculated those 3 dots and then just made a rough sketch from there. Now to get those points of intersection, you can do that algebraically also without having to have a graph. You don't need the graph. You just set these two equations equal to each other. 2y minus y squared equals -y. I move the y over to the left side. Don't ever divide by a variable. That's wrong. You never want to divide by a variable. Get the variables all on one side, then factor. So you end up with 0 and 3. So even without the picture, you can get this 0 and 3 pretty easily algebraically. And you can see from the picture here that the parabola is on the right and the curve is on the left. So it's going to be the parabola minus the line. Parabola minus line. And from 0 to 3. Let me jump down here for a second. I'll come back and show you that mess right there. But let's finish this and I'll scroll back up there. So it's right minus left from 0 to 3. I worked it out manually. That's fine. Put it in the calculator. Now, see, notice I use y. I don't know why. When you're just doing an antiderivative in the calculator, you use any variable you want. I don't know why I changed that to y. But if you put x in there, it's going to calculate the same antiderivative. It doesn't matter what variable it is. And so that was not necessary for me to call that variable y. But notice that I did, though. I put y there. That means you got to put y here. So if this is x, you put x here. And of course here I just did it with x straight out. So it's still the same basic idea. And either way, it's 9/2. 4.5, 9/2 is that area. But what I'm showing you here is actually, if you were trying to graph that in the calculator, it's actually for this one, not every one of them, it's kind of messy. Not for the x equals -y, that's just y equals -x. But look what I had to do. I had to complete the square and do all this business, and I came up with these two equations right here. First one, second one, and then y3 equals -x. And you kind of see there's a little gap there. Technically it's supposed to connect. Sometimes when you graph them separately like that. So what I had to do is, because you can't graph, because the calculator only understands y as a function of x. And of course that sideways parabola is not y as a function of x. So what it does, it creates the top half of that sideways parabola and then the bottom half of the sideways parabola. For this problem, I wouldn't have wanted to go through all this. I just would have done what I did before, is make the rough sketch, plot a couple of points, and just get a general feel for which way it's going. So you see that was kind of messy for that one, having to complete the square. And now this is just more, okay, also this is something that's useful for those moving on to Cal 3. Just kind of mentioning, somebody said, well, suppose we did that and you wanted to do it as y in terms of x. How would you, instead of x in terms of y? Well, this is also kind of a little bit messy here too, because for this particular region of integration, now notice as you're coming along here, if you're looking at it the way we normally look at it with vertical rectangles, you look at it, okay, the upper curve all the way to this end is the same thing. It's that graph right there. But look at the bottom. For this whole region, the bottom all the way up to 0 is the line, and then the curve takes over after the line. So you would have to treat, that's why I have two rectangles there. You have to treat that as two pieces. Now, of course, I'm using this right here where, y in terms of x, because 1 plus the square root of 1 minus x is the upper half of the graph, and then 1 minus will be the lower half of the graph. I didn't bother to work this one out. I just put it in Maple and let Maple do it. So I had to take that y as a term of x and come up to here from -3 to 0. 0 is where the bottom changes position, is at 0. So -3 to 0, it's the curve, the upper part of the curve, which is this, minus the line, which is -x, plus over here, it's the upper part of the curve minus the lower part of the curve. Upper minus lower. And I just happen to combine those algebraically because here I didn't, but the terms don't combine. Nothing combines on the left one. The negative of -x just becomes +x. And this one combines to this. And look at put it in Maple. And, well, look at the answer. 9/2. That is correct. But as you can see, that was really, really a pain to do it that way. Really not recommended when integrating right minus left was so much easier. Once again, this is a skill that's used in Cal 3 that it's deciding which is the easier path to take. All right. Okay, like I said, for these sideways graphs, I'm only going to use parabolas and lines. This one just happens to be two parabolas. One of them, and like I said, I'm guaranteeing only one region of integration. So it will not be two separate integrals added together. Now, see that last example I showed you, though, x in terms of y, it was only one region. It became two regions whenever I changed it, y in terms of x, which was not desirable. So knowing that this is going to be one region, notice I don't even have the picture drawn. I'll scroll down and show you the picture. And like I say, if you do this right, if you can get it backwards, just know the answer is going to be positive. The positive y squared means the parabola opens to the right. -32 minus y squared means that one goes this way. Now, of course, these graphs are going to connect. Obviously, don't let that. That's not. I'm just showing you the general shape. So now I'm trying to find. So these are they're going to kind of connect, like they're going to overlap like this. I'm trying to find those y values without even a picture, just algebraically, setting those two equations equal to each other, and you get plus and minus 4. That means the lower value is -4, right there, and the upper is +4. So you see, no official graph yet. I didn't do anything. So now I'm going from -4 to +4. Now, to know that I'm going to get this right the first time, that I'm going to worry about changing it from negative to positive, is the rule is right minus left. So the one with the negative y squared is right, so it's always on the graph will be on the right because it opens to the left. So this will be the one on the right, and then the one that opens to the right will be the left graph. So it's 32 minus y squared minus the y squared right there. All right, pretty easy integral. You can do this manually. Of course, you don't have to, but you work it out. You get 512 over 3. And then F and N, both the old way and the modern way. What do we have? We have, so you see I just used X here in the calculator, which is fine, obviously. Just do the integral, doesn't matter. And I did the math frac at 512 over 3, so there it is, negative 4 to 4, 32 minus 2x squared instead of y squared, same thing. 512 over 3, the answer is 512 over 3. But there's how you have to graph it. If you wanted to graph it in the calculator, you have to create 2 equations for one of them and 2 equations for the other. Frankly, I find that more trouble than it's worth. But if you notice, Stewie's head fits in there pretty good, doesn't it? How about that? And yeah, so you have to, but there's what it looks like. And I'm just mentioning that the scale for the x is 4 because this goes all the way out to like 32. On the x-axis. See, we were integrating the y is normal, but we're integrating from negative 4 to 4. All right, looks like I just brought back one more trig example here, just for the heck of it. Since I know how much everybody loves trig, right? Probably not. So negative 4 sine of x, sine of 2x, and as I said before, on these trig functions, just like I said for those y, x in terms of y, these only be one region of integration. The only time that you'll ever have more than one is if it possibly is if it's a normal, y as a function of x. That's not trig. But these kind, I just want to keep them one region of integration, not to get too messy. So if we're going from 0 to pi. I just chose for graphing purposes. I did graph it. I just chose pi over 2 as the breakdown for this one. Yeah, this one's a little bit different because you don't have, like I was talking about the common denominator idea earlier. I guess, I could have just gone straight from 0 to pi, but it doesn't matter. I've already done it, so I'm not going to do it again. But anyway, and like I said, if you don't want to graph this, knowing the fact that I said it's going to be one region, is you can put something like between the two, like pi over 2, without even seeing the graph, and whichever one's the upper will go first and the lower will go second. So you put pi over 2 in here. Sine of pi over 2 is 1 times negative 4 makes negative 4. Over here, sine of pi over 2. 2 times pi over 2 is pi. Sine of pi is 0. So 0 is greater than negative 4. So that means sine of 2x would go first. So it's sine of 2x minus a minus sine of 4x, which of course changes those to plus, 0 to pi, minus, so the antiderivative of sine of 2x, remember we saw that earlier up here. Like I said, if you learn these, quickly, like right there, makes your life much easier. So automatically, without using any kind of substitution, that becomes negative 1/2 cos of 2x, antiderivative of positive sine x, antiderivative, not derivative, antiderivative will be negative cosine 4 cosine of x. Yeah, a lot of people get confused there. Yes, the derivative of sine is cosine, but the antiderivative of sine is negative cosine. Plug in pi, plug in 0, and I worked it out manually. You got 8. F and N in the calculator got 8. I didn't put the modern version of the calculator in there. There's the graph just to see it. And then there we go. So the answer is 8. And that concludes the video on area between two curves.